Coming to transformer losses, transformer mainly consists primary copper winding, secondary copper winding, and transformer core. Major losses are copper losses on the primary side, copper losses on the secondary side, and iron losses. These are with reference to transformer core. Iron losses are hysteresis losses and eddy current losses. Other minor losses are stray load losses and dielectric losses. Iron losses are mainly eddy current losses and hysteresis losses. Eddy current losses are more than hysteresis losses. These iron losses are constant from no load to full load. This is only 3% of total losses. So these iron losses can be neglected. Eddy current losses are because of the circulating currents in the transformer core. This is the formula for eddy current losses. This is constant V maximum square, frequency square, thickness of sheet steel square, and total volume of the core. Losses are considered in watt or kilowatt. T is the thickness of laminations. Thickness of lamination can be varied from 0.3 to 0.5 mm. V is the total volume of the core. Here we are considering silicon steel laminations. We can go for CRGO sheet steel laminations also. As the quality of the material increases, maximum flux density of the core increases, so size of the transformer decreases. Effect of thickness of sheet steel laminations on the eddy current losses. If we reduce the thickness of laminations, resistance of these laminations can increase, so circulating currents will decrease, and the final result is eddy current losses will also decrease. Eddy current losses are directly proportional to conductivity. These eddy current losses can be minimized by adding 4% of silica to this silicon steel laminations. The approximate quantity must be 4%. If we add more than 4% of silica, then the core becomes brittle. So there are chances of breakdown of these sheet steel laminations. So for that reason, the addition of silica is limited to 4%. Hysteresis losses. Our transformer core, this is a ferromagnetic material. So when the transformer core receives magnetic flux, then the transformer core's dipoles, these are the dipoles. These dipoles try to orient as per the flux direction. This is the influence of magnetism on transformer core. As we know that the transformer core consists dipoles. These dipoles try to align as per the flux direction. During positive half cycle, these dipoles try to align in one particular direction. During negative half cycle, these dipoles try to align in opposite direction. This is sinusoidal flux waveform starting from 0 millisecond to 5 millisecond, which reaches the positive maximum half cycle, and from 5 millisecond to 10 millisecond, it reaches zero line again. From 10 millisecond to 15 millisecond, it reaches negative maximum half cycle. From 15 millisecond to 20 millisecond, it reaches zero line again. This is the waveform for 50 Hz frequency. That means for one cycle, the total time period is 20 millisecond. So for half cycle, it is 10 millisecond. We have different ferromagnetic materials such as dia, para, and ferro. For all these ferromagnetic materials, if we take the ideal condition and we draw BH curve for this ideal condition, this is the BH curve. V and H. V is the maximum flux density, H is the strength of flux. So starting from 0 millisecond, it is at origin. At 5 millisecond, it reaches positive maximum cycle. Till 5 millisecond, the curve is linear. And from 5 millisecond to 10 millisecond, as the flux changing from maximum positive half cycle to 0, the curve follows the same linear line and comes back to 0. At 10 millisecond also, it is coming back to origin. Similarly, from 10 millisecond to 15 millisecond, it is linear but in third quadrant. And from 15 millisecond to 20 millisecond, and it follows the same linear line and comes back to origin. This has to be the ideal case. But the time period is very small, such as 10 millisecond. So within the 10 millisecond, all these dipoles must be aligned as per the flux waveform for positive half cycle and negative half cycle. So all the dipoles will not change at the same time. So all the dipoles are not changing their orientation at the same time. So the BH curve is like this. At 0 millisecond at origin and 0 to 5 millisecond, the curve is almost linear. But from 5 millisecond to 10 millisecond, as the all dipoles are not changing the direction or orientation at the same time, so the curve takes different path. At 10 millisecond, the H is 0, but B is not equals to 0. This portion is retentive force. This is the retentive force. This is because all the dipoles are not changing their orientation at the same time. From 10 millisecond to 15 millisecond, the flux is in reverse direction. So this is the curve and it reaches the maximum negative value in third quadrant. From 15 millisecond to 20 millisecond, it has to comes back to origin. So this is the line. It takes the different path. This is the curve for one cycle. So starting from 0, 5 millisecond, 10 millisecond, 10 to 15 millisecond, 15 to 20 millisecond. But the ideal case was like this. It has to start from origin, goes linearly, comes back to 0 and goes linearly in third quadrant and comes back to origin. But in practical cases, because the dipoles are not changing their orientation at the same time, this is the curve. This is one loop for one cycle. Area under the curve is considered for one cycle and the same is multiplied with the frequency so that we can get the total hysteresis losses. In this case, V lags the H. This is termed as hysteresis. At zero crossing line, the core is demagnetizing and during positive maximum half cycle, the core is magnetized and the dipoles are aligned in one direction, and at negative maximum half cycle, the core is magnetized but the dipoles are aligned in opposite direction. At zero crossing, again the core is demagnetizing. So this is the cycle for heat generation. The core is getting magnetized and demagnetized, and there are hysteresis losses for one loop, for one cycle. So this causes heat in the transformer core. So this process, magnetizing and demagnetizing of iron core, orientation of dipoles changes from one direction to other direction as per the flux waveform. So this causes slight changes in the dimensions of the core. This is also termed as expansions and contractions of iron core. This can be approximately vibration or humming noise. The technical name for this is electromagnetostriction. This noise is measured in dB. It has to be measured from the edge of the transformer at 1 meter level. So what may be the approximate noise? This has to be as per the standards. Hysteresis losses formula. This is constant. Vmax 1 to the power of 1.6 frequency, and this is core volume. Units are in watts or kilowatts. These are important results from the hysteresis losses and eddy current losses. B maximum equals to voltage per frequency. If B maximum is constant, if B maximum is not constant, what are the effects on the hysteresis losses and eddy current losses? First, we are considering hysteresis losses. If we take B maximum as constant, then this total term can be taken as constant. So finally, this is A term as constant and frequency. So hysteresis losses are directly proportional to frequency. When B maximum is constant, hysteresis losses are directly proportional to frequency. Second case, when the B maximum is not constant. So from this hysteresis losses, V maximum is V by F. V is the voltage e to the power of 1.6 divided by frequency power 1.6. Here we have one more frequency term. So finally, this is constant into V power 1.6 volume of the core frequency power minus 0.6. So finally, this is a constant term. This is voltage term. This is frequency term. So when V maximum is not constant, the hysteresis losses are directly proportional to some constant voltage power 1.6 frequency power minus 0.6. So when B maximum is not constant, hysteresis losses terms depends upon voltage and frequency also. This is with reference to hysteresis losses. Hysteresis losses can be minimized by choosing better material, SS material or CRGO material. As we take best material, the maximum flux density can be improved. Eddy current losses when B maximum is constant. This is the formula. Constant B maximum square, frequency square, thickness square, and volume of the core. When B maximum is constant, we can take all these as constant. So the B is constant term and directly proportional to frequency square. So when B maximum is constant, eddy current losses directly proportional to square of the frequency. When B maximum is not constant, in this formula, B maximum is replaced by voltage per frequency, and there was frequency square term and frequency square term. These two get cancel each other. Finally, this is constant and this is voltage square. So when B maximum is not constant, eddy current losses directly proportional to voltage square only. So this term is independent of frequency term. This is very important result. Separation of hysteresis losses and eddy current losses. This can be done through open circuit test, but from the results we are taking here, hysteresis losses are directly proportional to frequency, eddy current losses are directly proportional to square term of frequency. Here we are considering B maximum as constant. So totally iron losses equals to hysteresis losses and eddy current losses. A is the constant term and frequency, B is the constant term and square of frequency. From this equation, we are taking frequency out. So iron losses divided by frequency equals to A plus B F. A can be taken as constant term and B is tan inverse of B. This is total iron losses divided by frequency and this is frequency. This can be the approximate graph for separation of iron losses pH and PE. P maximum directly proportional to V by F. P maximum can be maintained constant by varying voltage and frequencies in proportionally, or the frequency term and voltage term can be varied independently. The frequency can be varied with the help of cycloconverters and voltage term can be varied by motor and generator set. copper losses of transformer 75 degrees. This is the standard operating temperature of transformer. The total copper losses are x square to Pc. Here x can be 1 when it is at full load. X can be half when the machine is at half full load. So the transformer copper losses directly depends upon load. Total copper losses with reference to primary. This is the total resistance with reference to primary. This is the total resistance with reference to secondary. The total copper losses we can take either on primary side, we can take either on secondary side also. If you want to convert this total copper losses into per unit quantity, then this one has to be divided with E1 by I1. In per unit quantities, we know that R01 can be converted into per unit quantity when multiplied with I1 by E1. Similarly, for converting total copper losses into per unit quantity, this one has to be divided with E1 by I1. This is the graph for copper losses with reference to load. When the transformer is full loaded, copper losses will be 100%. When the transformer is half full load, the percentage of copper losses will be 25%. Stay load losses and dielectric losses, these are minor losses. So stay load losses, these losses depends upon load current. This is total 0.5% of total losses, so this can be neglected. This total stay load losses can be considered on transformer tank wall, nut bolts and conductor size also. If we take solid conductor, then there is a possibility of circulating currents in these conductors. This will cause flow of eddy currents in the conductor copper parts. So these are responsible for stay load losses. This can be minimized by replacing these solid conductors with stranded conductors. So in standard conductors, the eddy current are minimized and skin effect also minimized. Cross-sectional area of conductor. This is port 1, V1, I1. This is port 2, V2, I2. The total current in the transformer depends upon load. For example, here considering maximum load, so the rated current on the secondary side and the rated current on the primary side. So for the total rated current, the copper cross-sectional area or square mm has to be selected. This conductor shall suit the maximum peak current also. For example, here we are considering a transformer 40 by 50 MVA transformer. The 40 means when the transformer is fully loaded under normal condition. 50 means when the transformer is suitable for delivering the 50 MVA load for very short time. This is during peak condition. So the conductor size on primary and secondary will be selected as per the 50 MVA rating. Electric losses. This is the transformer core. Next to this transformer core, there is LV insulation, next LV winding, next HV insulation, finally HV winding. So these are the LV insulations and HV insulations. These insulations are selected as per the rated voltage. The total dielectric losses in insulation and transformer oil, these are only 0.25% of total losses. So this can be neglected. These dielectric insulating materials must withstand impulse voltages also. There is a thumb rule for this. Withstand voltage capacity of insulations. For voltages up to 11 kV, the insulation withstand capacity must be V into 2 plus 1. For example, if the insulation is for 11 kV, then the insulation must withstand 11 into 2, 22 plus 1, 23. That means up to 23 kV, the insulation should not fail. After 23 kV, the insulation may fail. This is the thumb rule. Similarly, for voltages more than equal to 33 kV, For this, the thumb rule is V into 3 plus 1. For example, if we take 33 kV insulation, for this, the withstanding capacity must be 33 into 3, 99 plus 1, 100 kV. So the 33 kV insulation must withstand up to 100 kV voltage. After 100 kV, the insulation may fail. Here we are considering one transformer. LV is 3.3 kV, HV is 11 kV. Now our available supply voltage is 3.3 kV. In this case, the transformer will operate normally without any issue. With the same transformers, HV side is connected on 3.3 kV side. Then the voltage induced on the secondary will be 1 kV only. That's because the applied voltage is only 3.3 kV. If we apply 11 kV, then on the secondary side we can get 3.3 kV. But here we are applying reduced voltage. That means only 3.3 kV we are applying. Similarly, as proportionate, only 1 kV will be induced on the secondary. That's because voltage per turns ratio is 3.3. So the secondary voltage will be only 1 kV. So the induced voltage on the secondary is lesser than the rated voltage. In this case, the insulation will not get damaged. On the other case, if the available supply voltage is 11 kV and we are connecting the transformer in this way, the HV is connected on the 11 kV and on the LV side we can get 3.3 kV voltage. The turn ratio is again voltage per turn ratio is 3.3. If we connect 3.3 side on the 11 kV supply side, then the voltage induces on the secondary will be 36 kV, which is very much high than the rated voltage 11 kV. So now we have to check whether this insulation will withstand its capacity or not. 11 kV, the thumb rule is V into 2 plus 1, 11 into 2, 22 plus 1, 23. Up to 23, this insulation will withstand. But the voltage is 36. This insulation will definitely fail. So this is the danger condition. Insulation will definitely get damaged. So here we have considered a transformer. LV side is 3.3 kV, HV side is 11 kV. We connect the same transformer on 3.3 kV side and 11 kV side, there is no issue. When available supply voltage is 11 kV, in that case, if we connect the 3.3 kV on 11 kV side, then the induced voltages on the secondary side is 36 kV. In this case, the HV insulation is at higher risk. It may get damaged. So the transformer connection and the insulation failure depends upon available voltage.